The process taking the partial with respect to y is very similar. Here, now the first term has only the z as a function of y, so I treat the x squared as a constant times, I don't know what the derivative of z is, so I just write it down dz dy, plus the second term is a function of, both of the terms y and z are functions of y, so I need to use the product rule. For the product rule, I take the derivative of the first term times the second term unchanged plus the first term unchanged times the derivative of the second term. I don't know what it is, so I just write it dz dx. So both of these together are the derivative of the second term. That's going to be equal to, now I'm trying to take the derivative of x, y, z with respect to y, but both y and z are functions of y, so I need to use the product rule. My x is unrelated to y, so I treat it like a constant. I just leave it out front. And I'm now going to use the product rule on y, z. The derivative of y with respect to y is 1 times the second term z unchanged plus the first term y unchanged times the derivative of the second term with respect to y. So at this point, I have a bunch of expressions with respect to dy, I'm sorry, that should have been a dy in the second place there. And I'm going to get all of the dz dy's by themselves and all of the expressions without a dz dy by themselves. So I'll move all the dz dy's to the left-hand side. I get x squared dz dy plus y squared dz dy equal, minus xy dz dy. And I'm going to move the 2yz to the other side. I get xz minus 2yz. I factor out my dz dy on the left-hand side. My right-hand side is unchanged. And then I divide through to get dz dy by itself. And I'm done. So that covers implicit differentiation. We'll move on now to second and third and fourth partial derivatives. Just like with regular derivatives, you can take partial derivatives repeatedly. The only thing that's different is that because you have multiple variables now, you have to be very careful to be explicit about which second derivatives and third derivatives you're taking. So here I'm going to take the second derivative, I'm going to take the first derivative with respect to x and y. I'm going to change notation here a little bit just for the sake of space. df dx can also be written f subscript x. Depending on your professor, a lot of professors tend to go this way. So I'm going to take the derivative with respect to x, and from here on out, I'm going to use this subscript notation. So now there are no implicit functions in this equation, so I'm treating my y's as constants. I get 3x squared plus, remember the y cubed here is a constant, so 2x times y cubed unchanged. And the third term does not have any x expressions in it, so I'm done. If I want to take the partial derivative with respect to y, my first term, x cubed, does not have any y's in it, so its derivative is 0. I'm treating the x squared as a constant, so I need to just worry about the derivative of the y cubed. So I bring down the 3, and I'm left with x squared times y squared. And then the derivative of the third term, I need to bring down the 2. I get 4 times y. Okay, so those are the first the first partial derivatives. I can take second derivatives of any of these things. And here's another just sort of notation note. When I take the second derivative, I'm thinking of this d dx as an operator, so something that I put out in front of everything to make something happen. So if I take d dx of d dx, I can write that d squared dx squared. Or I can write that f subscript xx. And you can see why people go with this other notation. I'm going to be interested in the second derivative d squared dy squared, which I can also write f sub yy. But I'm also going to be interested in what's called the cross partial derivative. So I'm going to be interested in d dx of d dy. I'm going to skim over this, but for your purposes, you should know that d dy d dx is exactly the same thing. Okay, so if I take the derivative of x and then the derivative, or say the derivative with respect to x and then the derivative of that with respect to y, I should get the same answer as if I do it first with respect to y and then with respect to x. And I'll go ahead and show you that that's true on this function. It is universally true, and your professors will assume that you know that. Okay, so let's go ahead and take the second derivative with respect to x. I get f sub x, and what that means is I've already taken the first derivative. I need to take the derivative of the first derivative. So this works exactly the same way as every derivative you've ever done before. You're just doing it a second time. So I'm going to take the partial with respect to x of this expression, 3x squared plus 2xy cubed. The derivative of the first term is 6x. The derivative of the second term, remember this y cubed is a constant, and the derivative of x is 1. So I'm left with the constant terms 2y cubed. My second partial with respect to y, well, I've taken the first partial with respect to y. I need to take its derivative again with respect to y. So I'm looking at this first derivative. I take its derivative with respect to y. This 3x squared is a constant sitting out front. For the y, I need to bring the 2 down. So I get 6x squared times y. And then for the second term, it's just minus 4. Let's go ahead and take the cross partials, starting with the 2 different starting points. So if I write it fxy, it means first take the derivative with respect to x, then take it with respect to y. So I've already taken it with respect to x. I have this 3x squared plus 2xy cubed. I'm now going to take the derivative of this term, except with respect to y. The derivative of 3x squared with respect to y is 0. There are no y terms there. The derivative of 2x times y cubed with respect to y, I bring down the 3. My x is a constant. I have 6xy squared. And I'm done. If I do the cross partial in the opposite order, I take the derivative with respect to y first, and then I take the derivative of that with respect to x. Well, this first term with respect to x, my y is a constant with respect to x, so I just need to bring the 2 down. I get 6x times y squared, and the derivative of the second term with respect to x is 0. So you notice that in this case, wow, that's a terrible line. Let's do that again. So you notice that in this case, these two terms are exactly the same expression. And that is a universal truth. It does not matter in which order you take the cross partial. The derivative should give you the same derivative in either direction. If you want to get really annoying, you can take the third derivative as well. So I can take f of x of x of x, which is now, well, I already have the second derivative with respect to x. I would take one more derivative of this term and simply get 6, because the derivative with respect to x of 2y cubed is 0. If I wanted to do the same with respect to y, I get y. Well, I look at this expression. The derivative with respect to y is going to be 6x squared. Okay? And notice that the rule we had before carries on to third derivatives. If I'm interested in f of x, y, x, so I would look at my derivative of fx sub xy, take the derivative with respect to x, get 6y squared. If I did the same thing here, now I have to be a little bit careful. Notice that I have one y and two x's. That's what matters. So I take the derivative here with respect to x. I get 6y squared. All right, so here's another example. Why don't you pause the video and work it out yourself? All right, so I'm going to take the first derivative with respect to x. I bring down the 3, I get 3x squared. My y to the 5th is a constant term. For the second term, I bring down the 4, I get bring down the 2, I get 4x. My y is a constant term, plus the derivative of x is 1. I take the partial with respect to y. My x cubed is a constant. I bring down the 5. I get 5x cubed, y to the 4th, minus the 2x squared is a constant. The derivative of y is 1, so I just have 2x squared plus 0 because there's no y in that third term. To take the second derivatives, I take the derivative with respect to x of the derivative with respect to x. So I'm starting with this first derivative. I'm taking its derivative with respect to x. I get 6x y to the 5th minus 4y plus 0. If I take the second derivative with respect to y, I bring the 4 down. I get 20y cubed, x cubed, and there's no y term in this second, or there's no y in this second term, so I'm done. And finally, if I want to get the cross partial, I take f sub xy, the partial with respect to x, and then with respect to y. My starting point is the partial with respect to x, so I'm now taking the derivative of this expression with respect to y. I bring the 5 down, I get 15, the x squared is a constant, y to the 4th, minus, I'm taking the derivative with respect to y, so I'm left with 4x, and the 1, of course, goes to 0. I could have taken the partial starting from my derivative with respect to y as well. So I take f sub xy. I'm looking at this expression now. I've already done with respect to y, so I need to do with respect to x. I'm going to bring the 3 down. So I get 15x squared. My y was a constant. And the derivative here with respect to x is negative 4x. And you notice that it doesn't matter the order that you did them in, you get the same answer. If I asked you this question on an exam, say, you only need to do one of those two, but it's not a bad way to check your work. If you're doing second derivatives already, you can do it with respect to x and then with respect to y, and you can catch a lot of mistakes that way. All right, so this was a long lecture with respect to second derivatives and partial derivatives. I encourage you to go back the very first week. There's a lecture about notation, and I'm going to repost it here because I think now we've talked about all of the notation that I mentioned in that lecture. It's a real quick, like 8-minute lecture. You might want to go back and review it this week because it references a lot of the different distinctions between the notations that we're using throughout this class. All right, so that's the end of the first lecture. The second lecture deals with concavity and graphing and all that good stuff.